Welcome back to Pi Academy. Today our topic is Cauchy's second theorem on limit and some application of this theorem. Statement: if sequence un be a sequence of positive number for all n and limit n tends to infinity un plus 1 divided by un equal to l greater than 0, then limit n tends to infinity nth root of un is also l. Now prove. Since L greater than 0, therefore we can choose epsilon such that 0 less than epsilon less than L, and there exists a positive integer capital N such that mod un plus 1 divided by un minus n less than epsilon, where for all n greater or equal to capital N. Since limit n tends to infinity un plus 1 divided by un equal to L, therefore by the definition of limit we can write this, and therefore or minus epsilon less than un plus 1 divided by un minus L less than epsilon for all n greater or equal to capital N, and we add L in the inequalities, we get L minus epsilon less than un plus 1 divided by un less than L plus epsilon for all small n greater or equal to capital N, and this is in equation 1. Now putting small n equal to capital N n plus 1 dot 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 small n minus 1 in equation 1, we get, first we put small n equal to capital N, then we get this, and when we put n plus 1 n minus 1, then we get the this in equation, we get this. Now multiplying the above n minus capital N in equation, we get here the number of equation is n minus n, because here n plus 1 to n, that is n minus capital N plus 1 and plus 1 equation. The number of inequation is therefore n minus capital N minus 1 plus 1. This is n minus capital N. This is the number of inequation. Then multiplying above all the inequation, we get L minus epsilon whole to the power n minus capital N, and this is when we multiply all these above, we get un divided by u capital N, and this equal to L plus epsilon whole to the power n minus capital N for all n greater or equal to capital N. We call it the inequation 2. Now taking the first part of the inequation 2, that is this part, we get n minus epsilon whole to the power n minus capital N less than un divided by u capital N. Therefore we get, from this we get this, and since epsilon 0 less than epsilon less than L, therefore if we put L in place of this, then this is less than this is greater than this. Therefore now from this and this we get this, and therefore we get L minus epsilon un L to the power n whole to the power 1 by n and less than un whole to the power 1 by. This is in equation 3. Again from the second part of inequation 2, we get similarly un divided by u capital N less than L plus epsilon whole to the power small n minus capital N, and this is L plus epsilon whole to the power small n divided by L plus epsilon whole to the power capital N. Then cross multiply, we get this for all small n greater or equal to capital N, and also L plus epsilon is greater than L, therefore we can write this less than this and less than this. Therefore from first and third we get un less than L plus epsilon whole to the power n, and this is u capital N by L to the power n. Therefore nth root of this is this, and nth root of this equal to L plus epsilon un by L to the power whole to the power 1 by n. This is in equation number 4. Now from equation 3 and in equation 4 we get L minus epsilon u capital N L to the power n whole to the power 1 by n less than this and less than this for all n greater than n naught, where n naught greater equal to small m. Where n naught greater equal to capital N. This is in equation number 5. Now since un divided by L to the power n is a fixed positive number, therefore limit n tends to infinity un divided by L to the power n whole to the power 1 by n, this equal to 1. Hence from 5 we get L minus epsilon less than un whole to the power 1 by nth root of un less than L plus epsilon for all n greater than n naught, and this equal to mod of nth root of un minus L less than epsilon for all n greater than n naught. Therefore limit n tends to infinity nth root of un equal to L, hence the result. Now there is some important examples on Cauchy's second limit theorem. The first example, prove that limit n tends to infinity 3n factorial divided by n factorial whole to the power n whole cube whole to the power 1 by n equal to 27. Let xn equal to 3n factorial divided by n factorial whole cube. Therefore xn plus 1 equal to 3n plus 3 factorial. We put n plus 1 in place of n, then n plus 1 factorial whole cube. Now xn plus 1 divided by xn is this, and we calculating this we get xn plus 1 divided by xn equal to this. Now because 3n factorial cancelled, n factorial whole cube n factorial cancelled, then the remaining is this, and we divide the numerator and denominator by n cube, therefore we get this. Now the limit n tends to infinity xn plus 1 divided by xn equal to 3 into 3 into 3, and this is 0 0 0, and this is also 0 because 3 by infinity, that is 0, and 1 by infinity, this is also 0. Therefore we calculate this 27. Hence by Cauchy's second limit theorem we can write limit n tends to infinity nth root of xn is also 27. That is limit n tends to infinity 3n factorial divided by n factorial whole cube whole to the power 1 by n equal to 27. Now there is another example. Limit n tends to infinity 1 by n factor whole to the power 1 by n. We have to find the value of the limit this. Let xn equal to n factorial divided by n to the power n. Therefore xn plus 1 is, we put n plus 1 in place of n plus 1 factorial divided by n plus 1 whole to the power n plus 1. Now xn plus 1 divided by xn is this, and we calculating this we get n to the power n divided by n plus 1 whole to the power n, and this equal to, we divide the numerator and denominator by n to the power n, we get this. Now limit n tends to infinity xn plus 1 divided by xn is this, and the limit of this is equal to e. Hence by Cauchy's second theorem, limit n tends to infinity nth root of xn equal to limit n tends to infinity 1 by n factor whole to the power 1 by n equal to 1 by e. Hence the result. Now question number 3. Prove that limit n tends to infinity n plus 1 n plus 2 dot 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 n plus n whole to the power 1 by n equal to 4 by n. Let xn equal to this. Therefore xn plus 1, we put n plus 1 in place of n, and then we get this. Now xn plus 1 divided by xn, this equal to, here xn plus 1 is, the value of xn plus 1 is this, and the xn is this. Therefore calculating this we get 2n plus 1 2n plus 2, because n plus 2 n plus 3 and dot dot 2n, 2n plus 1, 2n plus 2. From n plus 2 to 2n is cancelled. Here is also n plus 2 to 2n. Therefore, the remaining part is here 2n plus 1 and 2n plus 2. That is 2n plus 1 and 2n plus 2. And we get this. Therefore, limit n tends to infinity xn plus 1 divided by xn equal to limit n tends to infinity. Here we divide numerator this and this by n square. We get this, and similarly by n to the power n we get this. Therefore, the limit of this equal to 2 into 2, and the limit of this is e, and the limit of this is 1. Therefore, we get 2 into 2 divided by e, that is 4 by e. Hence, by Cauchy's second limit theorem, limit n tends to infinity nth root of xn equal to limit n tends to infinity xn plus 1 divided by xn equal to 4 by e, or limit n tends to infinity n plus 1 n plus 2 dot 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 n plus n whole to the power 1 by n divided by n is equal to 4 by e. Hence the result. And that's all. Thank you for watching. Please like, share and subscribe, and hit the bell icon to get all the notification of my new videos.